As you can remember, on our previous lectures, we have learned electrostatic field in vacuum or in isotropic dielectrics. And now it is necessary to learn some specific properties of conductors in electrostatic field. As you can remember, a conductor has free charges inside it. Free charges means that these charges may move. They may change. They may change their positions in space. Their position in space. So let's have a look at any. Let's have a look at some conductor in vacuum. Some conductor in vacuum. Let's imagine that there are some electric charge, free charge inside this. What will happen in this case? If we have electric charge and if we have electrostatic field, what will happen? If charge is free, there will be electrostatic force. There will be electrostatic force that is impressed on this charge, which is impressed on this charge. Electrostatic force, which may be described with formula. But because of electric charge is free, it will move. It will move, and there will be two possible cases. There may be two possible cases. The charge moves along a closed trajectory, or second case, charge will move until it appear on the surface of conductor. So let's consider these two cases more carefully. First case, charge will move along the closed trajectory. Is it possible? Is it possible to move along closed trajectory? In other words, electric current will happen. Is it possible? It is necessary to say that this is impossible. This is impossible in case of electrostatic field, because electrostatic field is potential field, and this means that linear integral along the closed trajectory is equal to 0 always for electrostatic field, and this means that work of electrostatic field will be equal to E and dr integral. It will be equal to 0, and when work is equal to 0, it cannot compensate loss of energy. But we always have loss of energy because conductor has some resistance, and it will be heated because of electric current. So energy loss will occur. Energy loss will occur if you have electric current in conductor. So motion along closed trajectory is impossible. There is only second case is possible. The second case is when electric charge will move until it appear on the surface of conductor. So there will not be electric charges. There will not be any charges inside conductor. And also there will not be any electric charges. There will not be any electrostatic field inside conductor. Okay, and what about electrostatic potential? What about electrostatic potential? We can remember that electrostatic potential is connected with electrostatic field by formula E is equal to minus gradient of electrostatic potential. And as you can remember, gradient is sum of derivatives. So if we write extended form of this formula, we will have sum of derivatives. dt, it will be not dt, it will be coordinates y and y j and plus d phi and d z key. And electrostatic field intensity. Electrostatic field intensity is equal to 0 inside the conductor. So it means that this is equal to 0. This is equal to 0. And of course, when derivative is equal to 0, the function is constant. It is results from calculus course. As you know from calculus course, if derivative is equal to 0, then a function is constant. So phi is equal to some const. So phi is constant. And the surface of conductor is also surface of conductor has also a constant potential. So the potential is constant in volume and on the surface of conductor. Constant means that it doesn't depend on coordinates. So the potential is constant value inside and on the surface of conductor. Okay, and what about What about electrostatic field near the external surface of conductor? Vectors vectors of electrostatic field will be normal to the surface. It is necessary. It is necessary because there there are no current. There are no current in electrostatic field. So electrostatic field, as we said before, electrostatic field cannot cause stable current. So it means that vectors of electrostatic field will be normal to the surface of conductor. I will try to draw this in some way. I'll try to draw this. So in each point, in every point of surface of conductor, vector of electrostatic field intensity will be normal to this surface. Will be normal to this surface. So it will look in some way like this. It is normal in every point. In every point. Okay, do you have any questions about this?
I understood. So far, so good.
Okay. Okay. So these vectors are normal to the surface of conductor. Because in opposite case, it will cause electric current, but it is impossible for electrostatic field only. So if you want to start some electric current in conductor, it is necessary to use something else, not only electrostatic field. We will discuss this later. So electrostatic field intensity is always normal to the surface of conductor. It can be written in this way. It can be written in this way. It can be written in this way. Okay, and what about let's imagine that let's imagine the situation when we remove some part of conductor from inner space of this, from inner space. So I will draw this again. So let's imagine that we have E is equal to 0, and charge Q is also equal to 0. And then we remove some part of this conductor from inside. So there will be some free space inside this. What will happen? The answer is nothing will happen. Nothing will happen. Why? Because we didn't have any charges inside conductor before, and then any charges will be removed from inside because they weren't be here. They weren't be here, so nothing will change, and nothing will change, and we'll still have E is equal to 0. Electrostatic field intensity will be still equal to 0, and electric charge is equal to 0. And electric charge is equal to 0 inside conductor. And moreover, if we put in some way additional electric charge into this inner space, it will move until it appear on external surface. So it will move inside conductor until it appear on external surface, and then there will not be any electric charge on internal surface of it. And let's try to find some more properties of electrostatic field near the surface of conductor in vacuum or in isotropic dielectric. So let's consider some surface of conductor, in vacuum or in isotropic dielectric. In this case, electrostatic field will still be perpendicular to the surface, perpendicular or normal, what is the same, and I'll draw this in this way. So electrostatic field is still perpendicular to the surface of conductor. So we can write this, we have the right angle. And let's try to find E is equal to E normal. Let's try to find the electric flux. From electric flux through the surface of infinitely small cylinder. I'll draw this cylinder in. I'll draw this cylinder here. No, it is not good. It is not good in this case. So I think I will extend this surface. I will extend this surface to improve my picture. I'll improve my picture. I'll improve my picture in next way. In next way, and here it will be more convenient to draw this cylinder, infinitely small cylinder. It is only geometrical surface, and because of this, I'll draw this with this cylinder with dash line. Dash line means that we have just some geometrical object. It means that it is not something. It is not something that exists for real. It is just geometrical object. Something that we imagine. Something that we imagine, but it doesn't exist. It doesn't exist, but it is useful. Sometimes it is useful to calculate what we need. And there this part of cylinder has area ds. The base of cylinder, upper base of cylinder has area ds. And according to Gauss flux law, I'll remind that it may be written in this way. Gauss flux law. Gauss flux law can be written as this: d multiplied by ds, and this is equal to electric charge, electric free charge or inside closed surface S. Surface S is shown with this dash line. So this is surface S. This surface S, and as we said before, the cylinder is infinitely small, and this means that instead of the integral, we will have just d multiplied by ds, and it is equal to dqs. Because the cylinder is infinitely small, so the surface S is also infinitely small, and we have electric flux because the cylinder is perpendicular to the surface of conductor. We have electric flux only through the upper base of this cylinder. And what can we say about this dot product? And we can say that according to the picture, vector d has the same direction as vector ds, because vector e has the same direction as vector ds. And vector E, and vector E has the same direction as ds, because we consider that we have electrostatic field in vacuum or isotropic dielectric. No, ds, d. In isotropic dielectric we have this. Why? Because we have learned before that d is equal to epsilon 0 E, where D is electric induction vector or electric displacement vector, and the connection between electrostatic field intensity and electric displacement vector is here. And when we have vacuum or isotropic dielectric, this will be just scalar. And because epsilon 0 is just scalar, we have this. So multiplying of vector by scalar cannot change the direction of this vector. So we have this conclusion, and from this we will get this conclusion, and this means that scalar product d and ds will be equal to d multiplied by ds and cosine 0 and cosine 0, and of course it will be equal to just to d and ds. It is necessary to take into account that we cannot always change scalar product of vectors by just algebraic product of its moduluses. But in case when two vectors has the same directions, we can do this. We can replace scalar product by algebraic product of absolute values of vectors. And from here and here, we have d multiplied by ds is equal to dqs. And from here, from this, we have that absolute value of electric displacement vector near the surface of conductor will be equal to derivative dqs and divided by ds and this derivative is equal to according to the definition, it will be surface charge density. Will be equal to surface charge density. So we have obtained that near the surface of conductor in vacuum or in isotropic dielectric, we have that D is equal to its normal component, and it will be equal to surface density of electric charge, or surface charge density. Surface charge density. And what about electrostatic field intensity? As we have said before, this is just scalar number. And if it is a scalar number, we can rewrite this for absolute value of vectors. In case where epsilon 0 are scalar numbers. And they are scalar numbers in vacuum or isotropic dielectric. Epsilon 0 E. Epsilon 0 E. And from this we will get that absolute value of electric field intensity, electrostatic field intensity, D divided by epsilon 0, electrostatic vector of electric induction, and it will be equal to sigma q divided by epsilon 0. Surface charge density divided by epsilon 0. So we have that electrostatic field intensity, or its absolute value, is equal to its normal component, normal to the surface of conductor, and it is equal to sigma q divided by epsilon 0. Divided by epsilon 0. Okay, do you have any questions about this?
It seems good. It's okay.
Okay. Okay. So and we can write the conclusion that near the surface of conductor, in vacuum or isotropic dielectric, near the vacuum or in vacuum or isotropic dielectric, or in isotropic dielectric, we have these two formula. Where sigma q, I'll write this, surface density, surface charge density. This is surface charge density. Is surface charge density. This is surface charge density. This is surface charge density. We have such formula for electrostatic field near the surface of conductor. Near the surface of conductor. So let's remove some formulas that we don't need more. And I'll also remove this. And let's have a look at some conductor with special form, like this, like inverted heart. So something like this, something like inverted heart, or heart that is put upside down, something like this. What will be interesting in this case? Lines of vectors of electrostatic field intensity are always perpendicular to the surface of conductor. We have discussed this before. So near the sharp part of conductor, here this is sharp part or spike or tip. So near this tip we have this. And here we will have a situation like this. But this also will be the right angle. So what will happen in this case? According to the direction of vectors, of electrostatic field, we can make a conclusion. That electrostatic field will push electric charges from here to the tip. And this means that the most of electric charge will be concentrated on the tip. So it is often used. This property is often used in some technical applications. For example, antennas or some defense of lightning. Are often made as a tip. So antennas and system of lightning defense often has some tips on it. It is made to concentrate electric charges near this tip and to increase field near near this tip. Okay, and do you have any more questions? No. Okay, so let's reconsider this conductor, but now we will consider the case of conductor in some internal electrostatic field. In some internal electrostatic field. What will be in this situation? In this situation, we still have that there will not be electric charges and electrostatic field inside this, and potential will be constant. But around this conductor, electrostatic field will be presented. It will be presented in around this. So we can write some lines of this electrostatic field. We can draw them. So we have something like this. This is lines of electrostatic field. I will show this E. Electrostatic field. Of course, in each point, these lines are perpendicular to the surface of conductor. And on the left side, we have similar situation. Here we have a very similar situation. So these lines are perpendicular to the surface, and it is necessary to write arrows to show the direction. And according to this picture, we can see that in this case, negative charges will concentrate on the left side of the conductor, and positive charges will concentrate on the right side of conductor because of the direction of electrostatic field. And this redistribution of electric charge on the surface of conductor is known as electric induction. This is electric induction. But despite of this, inside of the conductor, electrostatic field will be absent. And this property of absence of electrostatic field inside conductor is known as shielding effect. So shielding effect means absence of electrostatic field inside conductor. And this shielding effect is often used in some technical applications. For example, in coaxial cable. Let's have a look at the cross section of the coaxial cable. The cross section. Cross section means that means something like this. Cross section of coaxial cable. It has coaxial cable is a cable that is surrounded with some conductive shell with some conductive cover. So coaxial cable with conductive cover around it. So and it is necessary to show that the wire inside this cable is here. So it will be somewhere here, and this is a cross section of coaxial cable, and because of shielding effect, it is impossible to interrupt the signal transition through this cable. So shielding effect helps us to protect signal from some outside interruptions. Some outside interruptions, and this is an example of technical usage of shielding effect. And let's reconsider some conductor in vacuum. Some isolated conductor in vacuum, and let's consider that case when there are no any other conductors near it. Let's consider the case where other conductors are absent. So what will be in this case? We have already known that electrostatic field near its surface depends only on surface density, but the distribution of surface density in this case doesn't depend on free extra charge on surface. It doesn't depend on charge because the value of surface density depends on charge, but its distribution doesn't depend. So we can make a conclusion that sigma q is proportional. This sign means proportional to the charge q, and because of this, in this and this, we have that electrostatic field intensity is also proportional to the charge of conductor or extra charge. And What about electrostatic potential on the surface? We know that electrostatic potential can be calculated through the integral dr as phi, and because of this and this, we have that electrostatic potential on the surface of conductor in vacuum or in isotropic dielectric media is proportional to electric charge. Is proportional to free charge on the surface of this conductor. Is proportional to charge on the surface of this conductor. Okay, and what else can we say? This proportionality may be written in more convenient form. That Q is equal to C multiplied by phi, or in some other form, or it also may be written as capacitance. C is equal to Q divided by phi. This value C, this is a coefficient of proportionality. This value is known as capacitance. C is capacitance. This value C is capacitance. Is capacitance. And the units for capacitance are farads. Farad, this unit is was called by name of British scientist Michael Faraday, and in devotion to this scientist, we have unit farad for capacitance. So we have for conductor for conductor we can write a formula that we have such simple connection between electrostatic potential on the surface of conductor and electric charge. And what is important? It is important that capacitance doesn't depend on Q and doesn't depend on phi. It may look not obvious because we have them in formula, because they are connected by the formula, but capacitance is just only the coefficient of proportionality. So it means that if, for example, if Q increased 2 times, phi will always increase 2 times 2, and capacitance will not change. Okay, do you have any questions?
It's okay.
Okay, yeah, but we considered only isolated conductor. So we consider it conductor in case of absence of some other conductors near it. And what will happen? What will happen if other conductors appear near conductor that is considered? It will make some effect on electrostatic field around our conductor, and change of electrostatic field will change distribution of electric charges on the surface of conductor, and this redistribution will cause change of capacitance. So capacitance of conductor depends on absence or presence of other conductors or near the conductors that is considered. And on this effect is based some technical applications. For example, capacitive sensors, and capacitive touch screen on a tablet or iPhone. Capacitive touch screen is based on dependence of capacitance on present or absent absence of other conductors. And because our fingers are also conductors, our fingers may cause change of capacitance of some elements of capacitive touch screen, and because of this capacitive touch screen can feel when we put our finger near it. Okay, and the last question is will be the next. The next question is how to calculate capacitance in some particular case. We will look at example of some capacitive ball in a vacuum or in isotropic dielectric media. So let's draw this. Let's consider some ball with radius r. With radius r. And it has free extra charge on it. So this is radius r. And we know that we know radius. We know relative permittivity. If we have vacuum, relative permittivity is equal to 1, and when we have the electric media, relative permittivity is equal some special value for this media. And how to calculate the capacitance of this conductive ball. We know that according to this formula, it is necessary to set some charge Q on the surface of conductor and calculate electrostatic potential that will appear on this surface. So let's try to calculate this capacitance. So let's try to calculate electrostatic potential. To do this, we have to calculate electrostatic field intensity before. And to calculate electrostatic field intensity, the Gauss flux law will be useful. So let's use Gauss flux law. To calculate electrostatic field intensity around or near the surface of conductive ball. The surface integral d and ds is equal to qs. Where qs is electric charge inside the closed surface. And how to use Gauss flux theorem to calculate electrostatic field. There will be several steps. These several steps are the same for every problem. For every problem that may be solved by this theorem, by Gauss flux theorem. And the first step is choosing of the surface S or Gauss surface. So how to choose surface S? It may be chosen according to the symmetry of the system, and we have only three types of this symmetry. They are center of symmetry, the axis of symmetry, or plane of symmetry. Center of symmetry we have if we have point charge, if we have sphere, and if we have ball. So here we have center of symmetry. The second case is axis of symmetry, and we have axis of symmetry when we consider cylinder or charged line or charged straight line. So this will be axis of symmetry, and plane of symmetry when we have charged plane. So here we have the center of symmetry, and for the center of symmetry, the optimal surface S will be sphere. Why? Because sphere also has the center of symmetry, and I will draw this sphere by dashed line. Why dashed? Because this surface is not something real. It is just imaginary geometrical object. So this is surface S or Gauss surface. So this will be S. And we have to do two things. For this closed surface S, we have to calculate this integral, and we have to define charge inside this surface. And we have to define charge. Defining charge is simple because the all conductive ball is inside closed surface S. It means that all its charge is inside this closed surface. So because of this, we can make a conclusion that charge inside closed surface is equal to whole charge on the surface of the ball. Okay, and what about the integral? To calculate the integral, it is necessary to draw electrostatic field intensity vector or vector. I will draw this as vector D. Vector D. What is electric induction vector? Let's draw this, and as you can see, these vectors, vector D. This is vector D. It is always perpendicular to the surface of conductor in every point, and it will be also perpendicular. Will be also perpendicular to the surface, to the surface S, to this spherical surface S. So it will be perpendicular. So we have the right angle. Okay, what else? Maybe it is necessary to draw a radius of this dash sphere. Radius will be r. It will be little letter r. Okay, and what else can we draw? We can draw element of this surface. The element of this surface is ds, and it is always, according to the definition, is perpendicular to the surface, according to the definition. And from this picture, we can make a conclusion that vector D and vector ds have the same directions. And we know if two vectors have the same directions, the angle between them is equal to 0, and it means that d multiplied by ds is equal to absolute value of vector d multiplied by absolute value of ds and multiplied by cosine 0. Multiplied by cosine 0. And cosine 0 is equal to 1. So it will just be d multiplied by ds. So absolute values without vectors. So scalar product in this case may be replaced with algebraic product of absolute values of vectors. And this is very useful. This simplifies a lot our integral. And according to this, we can write that this integral will simplify to very similar integral, but without vector values in the integrand. Vector values in the integrand, and this is very useful for us. This is very convenient. And okay, and what about our next step? We have said before that we have a center of symmetry. It means that absolute value, for example, absolute value of vector d. Vector d is electric displacement vector. So d will be the same for in every point of surface S, and it means that d doesn't depend on ds. And because of this, d may be written outside of the integral, because it doesn't depend on differential ds. Doesn't depend on differential ds, and so it may be written outside of the integral. It may be written outside of the integral. And this, what is this? This is just algebraic sum of all elements of area of surface S. So it is just algebraic sum of elements of area. So if we add all of them, we will have just area of surface S. And because surface S is a sphere, we know its area. Area of a sphere is equal to 4p multiplied by its radius to the power of 2 multiplied by d. Okay, and do you have any questions about this?
It's okay for me.
Okay, so we can substitute our charge and this integral into the Gauss flux law, and from it we will get that 4p r to the power of 2d is equal to q. This is equal to q, and from here we have that electric induction, absolute value of electric induction vector, or electric displacement vector, is equal to charge of the ball divided by 4p r to the power of 2. 4p r to the power of 2. But to calculate potential, we need not electric displacement. We need electric field intensity. But we can remember that connection between them is d d electric displacement vector is equal to epsilon epsilon 0 e. Epsilon epsilon 0 e. And as we considered before that we have vacuum or isotropic dielectric. It means that this is just a scalar number. This scalar number. And it means that it may be rewritten for absolute values of this. For absolute value of this. And now we have that electrostatic field intensity, or its absolute value of electrostatic field intensity is equal to d divided by epsilon 0, and this will be equal to q, charge q, divided by 4 p epsilon 0 r to the power of 2. This is electrostatic field intensity. This is electrostatic field intensity, and this may be used. To define electrostatic potential on the surface of conductive ball. We need electrostatic potential to calculate capacitance. We need this to calculate capacitance. So let's try to do this. Calculate capacitance, not capacitance, electrostatic potential. We know that electrostatic potential phi may be calculated as linear integral from some initial point r0 to the point r e dr and plus phi 0. Plus phi 0. So in case when we have said before, in case if we have electric charges that are concentrated in some closed part of space or limited part of space, we can choose the optimal chosen will be r0 is equal to, or not equal, tends to infinity, and phi 0 is equal to 0. And because we need electrostatic potential on the surface of this ball, we have to put r is equal to radius of the ball. So we will have minus integral from infinity to r, e and dr. And this may be rewritten as r is integral from r to infinity, e and dr. E and dr. Okay, and how to calculate such integral? As you can remember from your calculus course, in general case, this integral depends on path between r and infinity. But we can remember that electrostatic field is potential field. If we have potential field, we have said this before, that if we have potential field, this integral doesn't depend on path that connects r and infinity. And this means that we can choose any path we want to. We can choose any path we want to. And let's choose this path. Let's choose this path to meet the condition. To meet the conditions that may be written. In this way. That may be written in this way. Let's choose some, and from this condition, this choice will give us will allow us to simplify our integral, because in this case I'll remind that we will get absolute value of E multiplied by absolute value of differential dr and multiplied by cosine 0. And this will be equal to just to E and dr. So we may simplify, because electrostatic field is potential field, we may simplify our integral. So we may rewrite this without vector values in the integral and in the integral limits. Integral limits. Okay, and now we can use our formula for absolute value of electrostatic field intensity vector. We can substitute this formula here, and we will get that integral from r to infinity. From r to infinity in integral function will be here, and the differential will still be dr. Charge q for p epsilon 0 doesn't depend on radius r, so it may be written outside of the integral. So we will have q divided by 4p epsilon 0 integral from r to infinity dr divided by r to the power of 2. Divided by r to the power of 2. And as you can see here, we have improper integral. It may be calculated if we rewrite it via limit. If we rewrite it via limit, like this. A limit like this. Lim some alpha tends to infinity, and the integral from r to alpha dr divided by r to the power of 2 divided by r to the power of 2. Okay, and what do we have? What do we have from here? This integral is simple. It may be found in some table of integrals. So we will have, it will be minus 1 divided by r, 1 divided by r, and the limits are equal to upper letter r and r equal to alpha. R equal to alpha. R equal to alpha. Okay, and now we can substitute integral limits, and we will have minus 1 divided by alpha minus 1 divided by r, and this is equal to 1 divided by r minus 1 divided by alpha. Minus 1 divided by alpha. And inside this limit, we have 1 divided by infinity. 1 divided by infinity, as you can remember from calculus, it will tend to 0. It will tend to 0. So it means that electrostatic potential is equal to Q divided by 4 P epsilon 0 R. P epsilon 0 R. So I'll remind that in this through these integrals we have calculated electrostatic potential on the surface of conductive wall in vacuum or in isotropic dielectric. In vacuum or in isotropic dielectric. And let's remember that capacitance is equal to charge divided by electrostatic potential. So we can use this. Capacitance is equal to electric charge divided by electrostatic potential, and this will be 4 P epsilon 0 multiplied by R. Okay, do you have any questions?
So it's okay for me?
Okay. So I'll write this capacitance. Capacitance of conductive ball. Of conductive ball it will be C is equal to 4 P epsilon 0 R, where R is radius of the ball. Okay, so if it is clear, uh, I should say thank you for your attention. Thank you for your attention, and I hope to meet you next week.
Thank you, teacher. Have a nice day. Have a nice week. See you.
Okay, have a nice day too.
Mhm.
See you later.